Hi, so like everybody else, thanks very much to the organizers for laying on this very enjoyable meeting. Oh, are we okay with the volume? It seems a bit boomy from here. Is it okay? Good. Okay, so this is joint work with Marcus, who is sitting there, and Johannes Zimmer, who is a professor of mathematics in Bath. And, well, I'll explain what the title's about in a minute. Some of this work was published in JSTAT-Phys, some of it was submitted about a month ago. So the main motivation for what I'm going to say is an observation from people doing sampling in statistical physics and Markov chain Monte Carlo in mathematics, and they find that it's good to consider sampling algorithms in which detailed balance is broken. That is, they consider sampling algorithms based on irreversible Markov chains. So I'll explain what all these things mean in a minute. And there are proofs that this should be a good thing to do, and in practice it seems to be a good thing to do, but we were not particularly aware of why it seemed to be a good thing to do. So it seems to be true that it works, but why would that be? And so what we're going to do is use a large deviation analysis together with a macroscopic fluctuation theory argument to try and come up with a sort of explanation for why this is true. And as part of that explanation, some interesting properties come out of rate functions and symmetries and geometry of what we're calling reversible and irreversible processes and their implications. And so this geometry is somehow more general than just this question, but it does at least help us answer this question, and we hope it may help us to answer other questions as well in the future. So that's what I want to say. So let's start with the motivation, and before the motivation, let's have some sort of setup. So we have some physical system, which we describe by some stochastic model, and we just imagine for convenience that we have some discrete states, some discrete configurations, which we're going to have labeled by curly C. So what's your favorite example? So an easing model or an exclusion process, or if you want something a bit more complicated, you can imagine a Markov state model of a biomolecule evolving in the cell, whatever. And we're going to have some transition rates, which I'm going to call, unfortunately, I'm going to call R from C to C prime. So R is for rate, even if many people would use W, but never mind. So this is the rate from C to C prime. It's not an escape rate. And in the steady state, the probability of state C is pi of C. So this stochastic model that we're thinking about, I'm thinking about some stochastic model of a physical system, it might be a realistic model of the dynamics of the system. So if you have an exclusion process, the idea is that the particles hop, and this represents how particles hop in real life. On the other hand, if you're doing Markov chain Monte Carlo, if you're doing sampling, you might have a Markov chain which describes some completely fictitious dynamics. It doesn't represent physical particles moving, but it's still a way to explore state space. So that's two possibilities for what this stochastic model might be. And then, so the title has in it detailed balance. Probably everyone in this audience knows what detailed balance means, but in case you don't, detailed balance means that the probability of being in C times the rate from C to C prime is the same as the probability of being in C prime times the rate from C prime to C. And if this is true, then the steady state of the model has a time reversal symmetry, which means if you play a trajectory forwards or backwards in time, you can't tell. Well, they happen with equal probability, so you can't tell which one is which. So systems with detailed balance are often used as realistic, dynamically realistic models of equilibrium systems. So this is sort of the first example. And they're convenient to use in Monte Carlo algorithms. So this is for describing dynamics. This is for sampling. So they're good models for equilibrium systems. They're nice, convenient models to use for sampling. And they have steady states without persistence current. That's what I already said. That's just time reversal symmetry. Systems without detailed balance are typically models for non-equilibrium systems. So if you want to study non-equilibrium systems, you need to consider systems without detailed balance. They're less often used in these sampling algorithms, and of course they have persistent currents in the steady state. So by comparing these two cases, our idea is somehow we can learn something about how to model non-equilibrium systems and what properties non-equilibrium systems have. And we can also learn how to design new sampling algorithms which exploit breaking of detailed balance. Okay, so there are these two things going on. There's somehow the physics of non-equilibrium systems on the one hand, and there's the questions of how to do sampling on the other hand. And these are related for reasons that I will explain. So just to have a real example, so everything, most of the talk is going to be very sort of a generic Markov chain with state C, but just to have something specific to keep in mind. So these were some simulations by Werner Kraut's group in Paris, and they were interested in the question of, suppose you take 1 million hard disks, and you put them in a box at a density of somewhere between 70 and 72%, so they cover about between 70 and 72% of the total area, they were interested in the question of what's the phase behavior of those disks. So what kind of order appears at high density? And in particular, at very high density, there should be some hexatic crystal. At low density, there should be a gas, and they wanted to know what happens in between. And they were able to resolve this question using computer simulations where other people had failed. And the reason they were able to do it was that they developed a Monte Carlo algorithm which didn't have detailed balance. And this, they say, gained them a factor of 10 or 100 in their sampling, which allowed them to do a problem which no one else had done before. And then people were they're like, oh, breaking detailed balance, we're not quite sure about this. So they went away and threw a large number of GPUs at the problem, and they solved it by brute force. So this was not a problem that couldn't actually have been solved by brute force, but nobody had. But indeed, they found the same conclusion, and they found that the breaking of detailed balance gave them significant acceleration to their dynamical scheme. But if you ask them, why does it work? Why does this method work? There's some sort of inertia that pushes you over the barriers or something. I mean, nobody really knows why this works. But we're going to give some kind of arguments now as to why it might be a good idea. Okay, so this is the claim. Breaking detailed balance generically speeds up convergence to the steady state, so Markov chain models without detailed balance tend to be more efficient. So what questions should be in your mind when people make grand claims like this? First of all, how are you going to compare detailed balance and non-detailed balance models in a fair way? And second of all, how are you going to measure this convergence to the steady state? So in order to justify this claim, we have to answer these two questions. So I'll answer these as preliminary questions. And then the real questions are, how much faster is it? What is the mechanism? And what does this tell us somehow from a physical point of view? Exactly. Or at least, well, we can do it in two ways, but that's the answer to the fair comparison. Well, then you construct a detailed balance model with the same steady state, and you compare with that. In principle, we're going to do this, right? So that's going to be the first question. So here's the first question. How should we compare? So these are the transition rates. There is, in general, no detailed balance. The steady state property is pi of c. Of course, you don't know it. But if you did know it, you could define a detailed balanced model with these rates, which would have the same steady state. And then we can say, well, it's fair to compare this model with this model. So whether or not we can construct this model, I don't know. But if we imagine that we could construct it, then we could compare. Does that answer your question? More or less. So there's two ways you might go around this. One, if you already know pi, you might try and construct the r's from the RS's. Or if you start with the r's, you might construct the RS's from the r. So you might construct the equilibrium from the non-equilibrium or the non-equilibrium from the equilibrium. Either way could be useful, depending on your situation. So that's the answer to the first question. This is the comparison we're always going to make between this process. Okay, and then how are we going to analyze rates of convergence? So the classical way in the literature to analyze the rate of convergence of Markov chain Monte Carlo methods is to use the spectral gap. So I'll say in a minute what the spectral gap is if you don't know. But with the definitions above, so with RS and R, the spectral gap of the non-detailed balance process is no smaller than the gap of the detailed balance process. That's a true fact. So that says that the non-detailed balance converges faster. And a whole bunch of people have worked on this problem. Percy Diaconis, Greg Pavliotis from London, Michele Ottobra, a bunch of other people. This is a sort of review which will contain a lot of the things that I'm going to talk about as preliminaries. That's the right question. So I'm kind of going to talk about this. I mean, but this proof is not very intuitive. I'll show you a sketch in a minute, but it's not very intuitive. And also, you don't really want to do spectral analysis if you've got like 1 million hard disks. I mean, it doesn't seem like a very good idea. So I'm not going to talk about spectral analysis, but just to give you a sense of how this works. So you have your master equation as usual. So the rate of change of probability of being in state C is given by this formula. You write this in terms of the generator or the forward generator or the transpose of the generator. You have a general solution. We're in finite Markov chains here, so you have a general solution just by diagonalizing where everything decays exponentially to the steady state with some eigenvalues lambda. And then we're going to define the dominant eigenvalue as the smallest of the minus lambdas. So the lambdas are all... What have I done here? Something's not right here, is it? But you can guess what's going to happen, right? So you want the smallest of these lambdas. And if all these lambdas are large, it converges quickly. Yeah? So that's the definition of the spectral gap. I'm sorry, something bad has happened with the signs here, but there should be a plus here. And now we're going to show that comparing the detail balance with the non-detail balance, the gap is always bigger for the non-detail balance process. Okay, and this proof I lifted from one of these papers, I've forgotten which one. Just very quickly, this is how it goes. So suppose that lambda is an eigenvalue of W, then you can just multiply on the right by the transpose of the eigenvector, and by pi, where this operator pi is just a diagonal matrix with elements that are the steady state, which are all positive, by the way. And then you take the real part, and you use that the definition of the master operator for the symmetrized process is just given by 1/2 of this this sum. And then if you look at this thing, you can kind of see you have some sort of Rayleigh-Ritz. This is like a variational thing, and pi is always positive, so there's no problem. And then you can show that all the real parts of all the eigenvalues of the W process are bounded inside the spectrum of the symmetrized process. Right? So this is just Rayleigh-Ritz for finite matrices, just the usual variational story. So the eigenvalues of the non-detail balance process have real parts that live inside the spectrum of the detail balance process in this sense. So this is the spectrum. These are the eigenvalues of the detail balance process. These are the eigenvalues of the non-detail balance process, and they all live in the same strip of the complex plane. Freddy first, and then Satya. Yeah, I'm in finite state Markov chains, right? Because I would like to keep things simple. I mean, for diffusions, you can do this. I don't see anything here that will fail if the gap is vanishing as the system size goes to infinity or something. I don't see a problem, but I mean, well, I guess the bound's not very interesting, right? If alpha s is going to 0, then you just have that all the eigenvalues are positive, which you knew anyway. Well, not so far as I know, but there are many things that I don't know about this. So this proof I lifted. Well, we put a proof of this in this short paper just for illustration, but it's proved many places. Okay, so now large deviations. Okay, so Spiliopoulos and Ray-Belay in 2014, they said, let's not think about convergence in terms of the spectral gap, let's think of it in terms of large deviations. And they proposed the following. So let's consider a trajectory over a long time t, and let mu t of r be the fraction of time spent in configuration r. So c has become r, but never mind. So mu t of r is the fraction of time spent in configuration r over a long trajectory. So as the time tends to infinity, convergence to equilibrium means that mu t of r should converge to pi of r almost surely. That's the usual large deviation story for ergodic systems, assuming now that the gap is finite. And you have large deviations, of course, which is the probability that mu t is about rho is bounded above and below by this exponential, on the exponential scale by this formula, which has in it the level 2 rate function. So this is called the level 2 rate function, and it determines the probability that you see some distribution rho, which is not the distribution that you ought to see pi. And this is literally what you do if you're doing Markov chain Monte Carlo, right? You take your set of samples, you compute an empirical average with respect to all your set of samples, which is just the same as averaging against this mu t. So this is exactly the object that determines your estimators when you do sampling. So that's one reason why this might be a good idea. So you're saying, what's the probability that when you sample, you observe a distribution which is not the distribution that you should have seen, even over a long time scale? So this I2, it's literally a rate function, right? Because this is the time, so this is literally a rate. And the bigger is I2, the faster is the convergence. So it's a rate. So I2, I said this already, I2 determines the probability that we see rho instead of pi. And now we can show, well, I mean, by a similar proof to the last one, we can show faster convergence for the irreversible process, or the same. I2 of rho is bigger than I2s of rho. So I2s of rho is the same rate function for the symmetrized process. So always we make the same comparison. And I'm not going to show this proof. I'll sort of go a long way round and come back to it at the end for a Markov chain. Okay, so it gets faster in terms of the spectral gap. It gets faster in terms of the rate function. There are proofs which you can read in papers, but they're not very intuitive. Somehow, how should we think about this? What's going on? So to get an idea, I'm going to go to this macroscopic fluctuation theory context, and then I'll come back to the Markov chains at the end. So I guess we've heard a lot about macroscopic fluctuation theory the last week or so, but just as a recap, so it's the theory of these gentlemen. So we now have a system of many particles hopping in real space, and we zoom out so we don't see the particles anymore. and we look at the density of particles instead, which is some smooth function, then we expect the density to follow this diffusion equation with a diffusion term and a drift. So I have chi for the mobility, which I think is what these guys have. Some people have sigma, but doesn't make a big deal. And E does not have to be a gradient of a potential, so it doesn't have to be a reversible Markov chain underneath. Okay? So just for an example, I think everybody probably knows this, but just for an example, we can have the weakly asymmetric exclusion process, particles hopping on a circle, say, at most one particle per site, hop rates 1 to the right and q to the left, and then we take the system size to infinity at fixed particle density, and we take q as 1 minus E over L, where E is the field. So we're in a weakly asymmetric case, and in this case, the deterministic current is just minus the gradient plus chi, which is this known mobility, and E is just a number. Okay. So for any fixed L, we have everything from before, right? Spectral gap gets smaller when we... Oh, so the detailed balance case is E equals 0, by the way, of course. So for any fixed L, we have the same results, that the spectral gap has to shrink when we turn on E, and I2 has to... Sorry, spectral gap has to grow when we turn on E, and I2 has to grow. Or at least they have to stay the same, because we never have... All these bounds include the equality. So the question is now, what happens when we zoom out and we look at the system from far away? So maybe it doesn't speed up anymore at all. I mean, maybe the speed up vanishes with large L. Who knows what's going to happen? So within the macroscopic fluctuation theory, we have formulae for these rate functions. That's one route to do it. So now let rho t be the time averaged density, and jt be the time averaged current. So this is the time averaged particle current. So this is the usual level 2.5 story for the experts who know. So I guess it's clear what these things are, right? So rho t is the number of particles in a certain region over a certain time, and jt is somehow a flux of particles through some surface. Then as time tends to infinity, you expect that the current should go to big J, and the density should go to the steady state density rho bar. So remember, pi was like the invariant measure on the Markov chain space, and rho bar is kind of like the steady state density on the macroscopic scale. So this is the formula for the large deviations of these observables. And it's very nice and simple. It's completely explicit. It's just given by the distance of J from what it should be squared divided by 1 over 4 times the mobility. And this is the spatial integral. And this is the time. So this is nice and simple because it's quadratic, and you can sort of look at it and you can sort of see what's going on. So this is called the level 2.5 rate function, as I said. And then, so remember, I2 is like our rate of convergence to equilibrium. I2 is the probability to see the density rho, which is not the typical density rho bar. So this can be obtained by contraction from this large deviation principle. You have to take the minimum over all currents J, which have no divergence. Because... No, he's saying something different. Can we take this discussion afterwards? So what I will say, for one thing I will say, so if I have non-interacting particles, then chi would be rho times d, and then we can agree we would have the same formula as the regular level 2.5. Okay, let's discuss offline. Okay, let me tell you what happens here, and we can discuss the naming later. Okay, so this is an analog of the level 2 rate function, which I'm going to call for the purposes of today I2, and it's obtained by this, and this gives you the probability to observe a density rho, which is not the typical rho. So, and obviously, the reason for this divergence being 0 is that we need a steady state current, which can't transport any density, otherwise it wouldn't be a steady state current. And this sets the probability of observing a non-typical density. So now we're going to show that this is bigger than this, so breaking detail balance accelerates convergence, just as before. But we're going to do this by some sort of geometrical construction instead of by algebra. So within macroscopic fluctuation theory, it's known that you can decompose the current, this is the deterministic current, as the current for the reversible model and the remainder. So this is the current that you get if you replace R by Rs and compute the hydrodynamic limit. So breaking detail balance corresponds to having finite JA. And we always compare models with fixed JS. That's equivalent to the fair comparison from the beginning. And the key point, which you can prove from the structure of the MFT theory, is that these two currents are orthogonal in the following sense. So you take JA, you take inverse mobility, you take JS, you integrate over space, you get 0. So this is not saying that the currents at any point in space are orthogonal. This is only true under the integral. But it is an orthogonality relation among the currents. So that's the first key feature of MFT that we need. And the second key feature is that the symmetric current follows the free energy gradient. So Js is minus the mobility times the gradient of the functional derivative of the free energy, where, well, the free energy is the free energy. So it's minimized at rho. So it could be also the quasi-potential. Okay, so this is all we're going to need. We're going to need orthogonality, and we're going to need gradient structure. So before I show you the proof, here's now the argument for why it's a good idea to break detail balance. So here's my contours of probability on the space of density profiles. So each point in this picture represents a density profile. This is the equilibrium state down here. And this is a nice convex space because we're on the macroscopic scale. Everything's very convex on the macroscopic scale. So if we have a reversible model, we have basically gradient descent in this space with a mobility. So where the gradient is shallow, the relaxation will be slow. And where the gradient is steep, relaxation will be fast. And we also know that the non-detail balance motion is perpendicular, orthogonal, to these arrows. So the non-detail balance motion does not take you at all towards the steady state. It takes you around the level sets. So it doesn't at all accelerate convergence downhill, because it's strictly orthogonal. But what it does is it sweeps the system away from these regions where things are slow, and it pushes it towards these regions where things are fast. So it stops you getting stuck in these very flat regions of the free energy, and it just takes you somewhere else. So for this whole construction to make sense, you need to define some sort of metric structure, which you can do. This Wasserstein metric story is not original to this paper, but it is described in this paper. Yes. So the problem is, of course, the non-detail balance motion can also sweep you away from the fast place and into the slow place. But on average, you always do better by breaking detail balance. That's the story. So this is my sort of explanation. This picture is what I'm saying is the reason that breaking detail balance is a good idea. Basically, it just takes you away from regions where the free energy landscape is very flat. So the spectral gap, I guess, is something about on average. The case of I2 is somehow uniform in rho. So for all rho, I2 is, whatever the statement is. This is true for all rho. So I'll say a little bit about that later. But you can sort of see that it's having an averaging effect. I guess this argument is what I say, that the spectrum stays inside the spectrum stays inside the detail balance spectrum. So in some sense, you're slowing down the fastest processes and you're speeding up the slowest processes. And what you care about is the slowest processes. So that's why you do better. But some of the really fast stuff that you might have got before, you might have destroyed. But yeah, on average, you do better. Okay, so here's now. So this is going to be the derivation. I'm sorry, Hugo, for the words. So this is what we have. We have this formula. We have that the current can be decomposed. We have orthogonality, and we have gradient structure. And now we want to show that this I2, which is defined as the minimum over J of this, is bigger for the non-reversible and the reversible case. So if you're, well, whatever, here it is. So let's start with the reversible case. So this is the 2.5 for the reversible case. It's this quadratic form. You multiply out the brackets. And then you remember that you want to minimize this under the assumption that this thing has no divergence. And you remember that this thing is nothing but a gradient. So 1 over chi times Js was exactly a gradient. So this term vanishes because you have a gradient and div j is 0. And so then you see that, and then you can do the minimization over j very easily, because this just set it to be 0. And then you see that the level 2 is just the modulus of Js for the reversible case. For the irreversible case, you have one more term. So when you multiply out, you have one more term or two more terms. So then you stare at this for a while. So this one is vanishing for the same reason as this one. This one is vanishing for reasons of orthogonality. And this one, it looks like you might be able to set J equals to JA. But you can't, because JA is not divergence free and you have to have J to be 0. But what you know is that this is definitely positive because this is a square. So you have that the 2.5 is this is nothing but I2S, and then this is something which is positive. And then you're done. So this is nothing but the argument that was in pictures on the previous page. It's just saying, because it's orthogonal, it sweeps you away from the steep regions. So we can get an exact formula for this speed up. Maybe I'll just show it very quickly, just as a sort of advertisement, maybe. So to compute this, you want to compute this minimization of occurrence, what you should do is you should add a force to the system that makes the density rho typical. And this is basically equivalent to these auxiliary processes, driven processes, optimally controlled processes, which you can find in all these papers. So it's a bit different from the usual thing because we're not doing a tilt here. We're just directly constructing the controlled process. But it's equivalent to this story. And in fact, you have to solve it. So you always have to solve the problem to get the phi. Getting the phi is just as hard as solving the problem. In this case, you have to solve a PDE to get phi, and it's just this PDE. Assuming I didn't make a mistake. And this current that lives in here is the steady state current of the controlled process. So I'm going to call this J tilde SS. It's the steady state current of the optimally controlled process. So you want to know the probability to see this rare density rho. You work out what is the gradient potential you need to add in order to get that rho. You work out the current that's flowing in that steady state. And then you have a formula for this infimum, which is just given by either this formula or this formula. So basically, this is an explicit thing for the speed up. It just says something to do with how much you have to control the process to get it to look like, to get the density to be rho. So this is the size of the perturbation that you have to add. So here's the picture now, the same picture as usual. Remember, these are contours of the free energy. So the probability cost to stay with some density rho requires that you resist both the gradient force that's going down and the orthogonal force which is taking you around. And basically, this is the probability cost that you have to pay to avoid being advected by the non-gradient force. So if you want to stabilize this density, you have to avoid being advected away from it by the non-gradient force, and that's how much you have to pay. So that's kind of an answer to Freddie's question, I think, is that you always more, because even if you were here, you'd still have to avoid the advection in order to stabilize yourself at any point on this surface. So when we go to Markov chains, you should think about this space as being the space of measures, not the space of configurations. That's the only thing to say. Okay, so that's the story. So we did, just to show you something, right? So these are non-interacting particles in 2 dimensions. We also did a zero-range process, or Marcus did a zero-range process in the paper. And this is a double well potential, because we thought double well potential is an interesting case. People often just do a Gaussian potential and check speed up for that. Well, you could do that, but we did a double well because maybe it's a bit more, maybe the convergence tends to be slow when you have a double well. And you can get a modest speed up. So this is reversible, irreversible, constructed, as we said. The irreversible has a sort of Hamiltonian-like drift around the contours of the energy here. And you get a speed up by about a factor of 2. So remember, all these bounds, they're just inequalities. You just have no idea whether it's really going to work or not. In this case, you get a factor of 2, which is a factor of 2. It's OK. Sorry? So it's like a Hamiltonian drift around the contours of the energy. So it is actually orthogonal to the gradient drift in this process. And how fast you can make it, there's an issue with positivity of your transition rates, which limits how much asymmetry you can put in. Well, this is basically equivalent to Hamiltonian evolution on the landscape, where the previous one was equivalent to diffusion. Well, Hamiltonian plus noise. Well, we could talk more about the example. I mean, I think it's an interesting example, but the main thing is just to say you're not guaranteed you get any significant speed up. You get a factor of 2, which is all right. You might have liked a factor of 10, but you don't get it. The thing to notice is, if you've got to cross the barrier, you've got to pay the probability cost to get onto the barrier. And because you've got a strictly the same invariant measure, you've always got to pay that cost to get onto the barrier. So all this is doing is it means that if you get to the right height, if you get to the right height over here, you're more likely to get over, whereas before excursions had to get the right height and in the right direction. So this is the average position in the x1 direction, and we started them, I think the origin's been shifted. So I think they were started in this secondary minimum over here, and then you measure just the average position of a cloud of particles as they cross the barrier from here to here. So we measured also relative entropy with respect to the invariant measure and various other things, and factor of 2 is about the same for all of them. I mean, it's not a very deep example, but it just shows that you get something. So, I don't know, seems sort of interesting to me. You have this orthogonality structure, you have this sweeping of the density away from the regions where things are flat, but it's all very specific to MFT. Juanpe.
Can I ask a question about the previous speaker?
Yes. Well, I mean, this thing has to be projected onto the spectrum in some way, right? So if this is a slow process, if it doesn't see whatever the fast process is, it doesn't care they've been slowed down. It's probably quite a slow coordinate, this, so I suspect it projects mostly onto the low modes. Yes, so does any of this... So I started with like a general Markov chain, right? So does any of this apply in a general Markov chain where you don't have these nice quadratic rate functions and everything? The answer is it kind of does. So within MFT, we have this quadratic rate function, which, just for the purposes of the next 3 minutes, I want to write as a norm. So this is just saying that it's a square, so I can write it as a norm. And then I have this gradient, and then I have this orthogonality, and I'm going to write this orthogonality as some sort of inner product in this norm that has to be 0. So if you try and do this analysis for a general Markov chain, then you don't have a square, so you don't have a norm, and you don't have an orthogonality. But you have something which looks a bit like an orthogonality, and you have something which looks a bit like a norm, and you have something which looks a bit like a gradient. And Marcus talked about these things last week, but let me just very quickly summarize how it goes. And if you want to ask questions, you can ask. So within macroscopic fluctuations, so let's cast macroscopic fluctuation theory in terms of forces instead of currents. So we'll write that J is chi times F, so chi is the mobility. So we're just going to do everything in terms of forces now instead of currents, and of course it's equivalent because chi is invertible. So now the rate function is the norm of the current minus the mobility times the force squared with a factor. The gradient force, the symmetric force is the gradient of the free energy, and the sum of the symmetric and antisymmetric forces squared is the same as the difference of the symmetric and antisymmetric forces squared. So this, if you multiply the brackets, just tells you that these two things are orthogonal. Okay? And then what we are calling for today the level 2 rate function is the norm of the symmetric current plus the norm of, this was, remember, the steady state current of the optimally controlled process, and this was the antisymmetric current. So these are the formulae that we have. This term is quantifies the speed up that you gain by breaking detail balance. So if we want to do Markov chains, we have to identify the forces. The force from going from C to C prime depends on the density rho, and it's given by this formula. So rho is some kind of empirical density now we can discuss. So the analog of this rate function is some function phi, which depends on rho, j, and f. It's non-negative, it's convex in j and f, but it's not a norm. But it has these properties of the squared norm. And it has some other properties as well to do with what happens if you change the direction of j, but we won't go into that for now. We have that the force is the sum of the symmetric and the antisymmetric, with the symmetric being a gradient. where this is just discrete gradient. We have a function psi star, which is definitely positive, should be bigger than or equal to. It's symmetric and convex in the force, so that's analogous to the modulus of the force squared. So this is like a generalized squared norm of a force. So it's not a square, but it has these properties. And then we have this property which says that if I plug in fs plus fa here, or if I plug in fs minus fa, I get the same answer. And this we are calling generalized orthogonality by analogy with this. And then you just turn the handle, and you sort of make a sort of lookup table, and you get a formula which looks almost exactly like this. So here you have something which is like a rate function for the symmetric case. So there's a slight modification to what the function phi you use, but it's just in the details. And then the modification of this squared norm is this object. Okay, so this is just to show you can make this mapping now. So even though it's not a strict orthogonality anymore, even though these geometrical things are not so sharply defined, it seems to make sense to generalize this picture now. Even though, as I say, even though nothing is so well defined, I think because of the analogy between the derivations, it makes sense to say that this mechanism is still operating, even for the Markov chains. Quick advertisement about this structure surviving if we have systems with finite damping. So instead of overdamped second order Langevin, you can do some of this stuff, and that's in this paper. So thanks for listening. Thanks for the questions. I'm sorry for causing trouble with giving things the wrong name, and I'm happy to have questions.
I think it's just not a question of naming, because you said your analysis actually helps us understanding the sampling efficiency, but I would claim it's not about the sampling efficiency, because we're not talking about the convergence in the ergodic theorem sense of the empirical distribution. So this is something we can discuss further on, but I think it's not just a question of naming and then confusion.
So for the Markov chains, I mean, we are happy, right? So for the Markov chains, this really is the level 2.5 now.
Well, yeah, but you cannot start from FFT up there, because it's not, you can make some analogies there, but I don't want to discuss that.
But I could do diffusions here. I could set chi to be rho times d, and everything would be the same.
No, but then the rate function is very different. Like, they look the same, but it's very different. And the main difference is that if you look at MFT, if I fix the current, I fix the density. They're deterministically related. In level 2.5, that's not the case. The empirical density can fluctuate. It's correlated to the current, but they can fluctuate on the two sides. You don't have this in MFT. It's just not the same object, but it's not the same framework of fluctuations either. In MFT, you have just the continuity equation fixing the density if I fix the current. It's only the current that fluctuates. And by the relation, the density will fluctuate too.
I don't agree.
But you have that constraint, that continuity constraint, exactly for the MFT. You don't have this for level 2.5.
You have a continuity constraint for level 2.5, which is that you have to set div j to be 0 always for level 2.5.
Yes, but the density, the empirical density itself can fluctuate. If I fix the density, if I fix the current, I'm not fixing the density. In true level 2.5, I still have fluctuations of the density.
I think you still do. I don't understand.
No. The second part, no. The first part of the talk where you say I'm doing MFT in order to get conclusions about level 2.5. This is where I object to. The rate function is different, but the fluctuations are different too.
But the first part could presumably be redone as a limit of the Markov process.
I'm not so
It's
sure.
not even redone. They're non-interacting particles.
So in the result I was talking about during the talk are different from what you. But basically, the beginning is the same. You have an equality for the evolution of the value of the quasi-potential, and it is related to the square of the gradient of the quasi-potential, or maybe in a norm. And then there is a next step, which usually involves the convexity of the quasi-potential, that allows you to actually bound what's happening everywhere in the phase space. So I guess that in cases like the one you were discussing in your example, for which you have a double well potential, this does not hold, and it's related. So I think that's why you cannot expect to gain a lot, because where the quasi-potential is not convex, then so it's basically in your case it's just passing through the saddle points. So this is where the slowest part of the process comes from. So sorry, my question is a bit fuzzy, but maybe you got the idea.
Yeah. So it would be, I mean, it would be great to hear exactly what is proven and where. I mean, I guess this example, they are hard spheres, right? So everything is entropy. So you can kind of imagine that it might work because there are not lots of big barriers, and maybe there's some collective modes that you can excite. And here it really worked well, and they got, you know, factors of 10 or more. I'm not sure what people think they can get by just, for example, using molecular dynamics instead of overdamped dynamics. I'm guessing it's factors of 2 to 10. I don't know of examples where people have managed to exploit this to really get a huge saving. But I guess the hope was maybe by understanding the mechanisms better, one can predict better things. So what about this Nesterov stuff, Grant? Do you think they can... I mean, there are examples of this kind of thing working well, I think. I mean, it's in the Kramer's prefactor, right? It's in the, or whatever we call it, yeah. It's in the prefactor, but the prefactor is still there, so... That's right. That's right. So in our example, I think we managed to drive a lot. So just to repeat what I said, sorry, just very quickly. Oh, come on. Where's the example? Yeah. So typically that you're in here, you want to get over this barrier. So what tends to happen is that one thing that can happen is that you wander up over here, and then the orthogonal drift kind of sweeps you around the level set and you're over, and then you can fall down again. Whereas if you want to get over with the diffusive dynamics, you have to set off in this direction and get up and down again. So you can get quite a good enhancement of the flux over the barrier, even though you don't get any gain in the exponential prefactor. And because it's not a very high barrier, I mean, this is what, can you see? 1, 2, 3. Probably the temperature is 1, so it's only a, well, it's here as well, isn't it? It's only a 2 kT barrier, it's not huge. So that's why you can get something back.
So you showed this general bound. You said something, it was that the rate function for the empirical measure of the non-detailed balance was bounded by below by the detailed balance. And I think that you're saying that this is general, and then you proved it in this MFT context, but the bound, I think, is the general state.
Sorry, yeah.
So, I'm just checking I understand. So that obviously implies that the fluctuations of all time integrals in the large time limit are smaller in the non-detailed balance problem that the... Is there an equivalent statement for the fluxes?
So the first statement in the jargon is called asymptotic variance. And that's, I think that was proven before the large deviation result. So they proved the asymptotic variance of these non-fluxes, of these configurational things, they are bounded. So that has been looked at for sure. For fluxes...
I mean, certain fluxes are directly related to time integrals.
So you mean variances of fluxes?
No, just the whole rate function means all fluctuations beyond variances.
Yeah, okay, so, but
Sorry?
well, you have a mean for a start. So there is no very simple...
Fluxes that are not directly related to time integrals. So, you know, it's one doesn't follow from the other. That's my question.
I don't think, I mean, there are the dissipation bounds, right, which you can use to bound currents.
No, I understand, but I try to understand this connection between the driven and the specific, you know, symmetrized process.
So yeah, I don't know of anything general. You can compute bound on the symmetric guy, a bound on the asymmetric guy, and compare. I don't remember what happens.
Okay.
One could check quite quickly.
Well, it's interesting because, you know, the stuff I guess you talked about last week and so on, that's, you know, that's bounds fluctuations from below. You know, fluctuations are larger than, you know, the bounds. It's about fluctuations being smaller than the bounds, but for this time integrated, the two things tally together.